Alright guys, welcome to our channel Code with Sunny, and today we will be discussing the medium problem of LeetCode. Insert into a binary search tree. Its index is 701. Okay, so as the name suggests, we have to insert a node in the given binary search tree. Okay, so where should we insert the node so that the criteria of binary search tree will still be like holding, for a particular node all the nodes lying in the left subtree would have the lesser value than the current node, and like strictly lesser, and all the nodes lying in the right subtree will have the value of strictly more than the current node. So we have been given the root node of a binary search tree and a value to insert into this tree. Return the root node of the BST after the insertion. That is when we have inserted the node. So you can see we are going to return the new root node. If the root node changes, we are going to return the new root. Otherwise we are going to return the same root after inserting the given value, like making the new node and inserting at a suitable position. It is guaranteed that the new value does not exist in the original BST. Okay, so notice that maybe exist multiple ways for the insertion. That is, you can insert in many possible ways. You can see, yeah, I will explain it out how this is going to be done. As long as the tree remains a BST, after insertion you can return any of them. Okay, and let's look over the constraint. It is around 10 raised to the power 4, so we'll be looking for O of n solution. Okay, so how this is going to be done, let's understand this one. Okay, so let me just pick it up this example. Wait a minute, it should be like this one. Yeah. Okay, so suppose this is the given binary tree, and we have to insert the value, let's say 5. Okay, so you can see, let me just choose another color. Yeah, and we have to insert the value 5. So you can see we need to after the insertion the criteria of BST must also hold. Okay, so there are many possible ways to insert the value 5. Okay, so the first way, the simplest way would be like, you are facing the value 4 and the current value is 5. You can see that all the values lying in the right subtree will have the value greater than this 4, strictly greater, and all the values lying in the left subtree will have the value strictly less than the value 4. You can see over here. Okay, and my current value is 5. You can see it is strictly greater than 4. So what we are going to do is we are going to find out the leaf node corresponding to this value 5. If you're not understanding it, let's try to traverse this tree and find it out. Where should we insert this position? You can see it is 5, here the value is 4, and we need to insert 5. So we'll move to the right node, right child node. Okay, now you can see the value is 7, and my value that should be inserted should be 5. You can see 7 is greater than 5, so 5 must lie in the left subtree of this 7. Okay, left subtree of this 7. You can see, but there is no not any node present in the left subtree of this 7. So here we are going to insert the node 5, and we are done. And still you can see the criteria of BST is satisfied. And there are more ways to insert this 5. You can make this new node 5 as the root node also. Okay, how this is going to be done, let's see. You can see this BST is also a valid BST when we insert this node 5, and this 5 becomes the root node of the new binary tree. Okay, so it is like, you are making this 5, and left node would be like 2, right node would be like 7, and here it should be like 3, and here it should be like 1. You are inserting the 5 as the root node, but you can see this process is quite complex. You can see the orientation of this BST also changes, so this is quite difficult to find it out, like to make a new binary tree and inserting the current value as the root node. But finding it out the suitable position at the leaf node side will be a easier way. So we would be doing, like, suppose the value, this is needs to be inserted in BST. So we will first find it out the correct position of this value, correct position of this value. Now we are going to find it out the correct position of this value. So we will compare with the current node. Compare with current node value. So there are only two possible cases. You can see if the current node value, let's say current is the address of this node, if current value is strictly greater than the value that we want to insert. Okay, so it means that we should move to the left subtree. Move to left subtree. So let's analyze this with a simple example. Suppose here you can see the current value is 4, and suppose we want to insert a value, let's say -1. Okay, so let's compare 4 and -1. You can see -1 is strictly less than 4. It means that you cannot move to the right subtree and try to insert this value -1, because this will violate the criteria of binary search tree. So we should always move to the left subtree, and we will try to find it out where -1 should be placed. Okay, and we would be stopping where we would encounter a null pointer, like you can see after this one, this is actually a null pointer. Okay, so there is not any node present over here, like that. Okay, and what about if you face current value, current node's value strictly less than the value that we want to insert? You can see this value that we want to insert is strictly greater. Suppose it is 5 and we want to compare it with the 4. You can see if we are not going to insert 5 to the any of the nodes for the left subtree, because it will violate the criteria of BST, so we'll be inserting into the right subtree of this current node. You can see we are going to move to this node. Again we need to compare, so the comparison will be done in the recursive fashion. So we will be iterating for all the nodes in a recursive way, and we will try to insert them at the suitable position. Now when we are going to insert this node, so whenever we will encounter some node, let's say you are at this node, and you will try to find it out, that we'll try to compare with the value that we want to insert. Suppose it is -1, okay, and the current node is value is 1. So we will check it out that where should we move. -1 is strictly less than the 1, so we should move to the left one, left child. But you can see that there is not any node present over here, and still we need to insert this value -1. So the correct position is to insert it over here. Okay, and what about if we are going to have the value, let's say 5, or let's say 6? So we will compare it from the very first. It means that 6 is greater than 4, so we should move to the right child node, and still you find it 7, and you can see that 6 is less than 7, so we should move to the left child node, but you are not going to find any child node, so the best position is inserting 6 over here. So 7's left child would be 6. So this is the correct position. So this is the simplest way to do this problem. So we are going to do this in both iterative and recursive way. Let's try to understand this one. Okay, yeah, so this was, I think, iterative one, but I will try to explain the recursive one first, because the recursive one is easier to grasp. You can see if root is null pointer, it means that we are done over here and still we haven't inserted, so we will return the new node by making a new node with the given value. And if val is greater than the root val is actually the value that we need to insert by making a new node, is greater than root val, we need to go to the right child node of the current node. Okay, so we will go to the right child node of the current node, and the node that is being returned will be the root's right. So we will assign it right up to here. Okay, so if you're not getting it, we will explain it. Suppose that we need to insert 5. Okay, so here it is 4, and it will compare with it 5. So you are going to go to 7. So it should be like 4's right. So 4's right would be assigned to some node by calling solve function. Actually it is solve, not insert into a BST. So let's call it as solve now, calling it solve function and passing the right child node address. So it passing the 7th address. Okay, so in the next recursive step, so we are at 7th node. Okay, and we will check it out, compare it with the value 5. So we'll compare it with the value 5. You can see So 7 is going to be greater than 5, so we will move to the left child node. Okay, so it should be like 7's left would be calling the solve function again and passing the 7's left. 7's left would be actually a null pointer. Okay, so you can see whenever we encounter null pointer, we will return a new node with the given value. So it will return the making a new node with the value 5 and returning it. So 7's left would become, so this function will return a node with value 5 with value 5. So this will be a node with value 5 and it will be the 7th left node. Okay, so you can see 7th left node would be the value 5 over here, which is actually inserting this node 5 to the left child node of the node 7, and every you can say every recursive step still balances the criteria of BST. And if val is strictly less than the current node's value, we will be going for the left child node. So this will be the recursive step. You can see the time complexity is O of n and space complexity is O of 1. And let's talk about the iterative one. Iterative one is also simple, but I think quite like for the newbie coders it will be quite difficult to implement, or maybe but still it is a easy one. Okay, so taking the current root node and like a new node would be like making this new node with a given value, and we will iterate until we find a that node whose either left child or right child is a null pointer and it is the suitable position to insert. So if val is greater than current value, it means that you need to go to the right subtree. So we will check it out. If current right is the null pointer, so this is the correct position to insert this new node. So I will insert it, current right become new node, and we are done. So we're using break statement. And what about if current right is not a null pointer? It means that it is a valid node address. We'll be moving to its right. Means we are finding out the suitable position. And if val is strictly less than the current val, the correct node position will be going to left child node. And if we are going to find our null pointer, we would insert it right over here and we are done. Otherwise, just traverse it more and find out the correct position. So after doing this one, you can see there might be some case like root is null pointer itself, because you can see the constraints are like this one. Like number of nodes in the tree would be starting with 0. So in that case, the root will be a null pointer. We need to make this new node as the root node. Otherwise, this root will be satisfied because we have inserted this new node at the correct position. So this will give you all test cases passed. So if you guys have any doubts, do let me know in the comment section of the video, and thank you for watching this video.